And when you're setting this up, the concept that it depends on is the concept of similar figures. Because when you look at this, two semicircles, just like circles, are similar to each other. That means that um, they have the ratio of parts and ratio of areas like we have looked at. So if the ratio of parts of two similar figures is m to n, the ratio of their areas is that ratio to the power of however many dimensions you're measuring. So area is how many dimensions? 2. So you're going to square that ratio. Okay, so when you look at this, if they tell you here the area of the rectangle is 81, and the ratio of the areas for these semicircles is 16 to 1. So when we look at this, the ratio of areas is 16 to 1. What does that mean the ratio of their corresponding parts, which are going to be the diameters here, are going to be? Well, to move from areas back to parts, you square root. So if we take the square root of 16 and the square root of 1, we have the ratio of one-dimensional parts to be 4 to 1. So for every diameter in this small rectangle, the larger, or the small semicircle, the larger semicircle is going to be 4 times that. And so if you look at the area of this rectangle, which is base times height, it has to equal 81. So if you solve this and solve for your d value, you can divide both sides by 4. And you get d squared is equal to 81/4. When you extract the square root here, square root of 81 is plus or minus 9. Square root of 4 is plus or minus 2. Since we're dealing with a measurable distance, you can only account for the positive roots of those. So 9/2 is this measure, which means this the diameter of the larger semicircle is going to be 4 times that. And so if you took 4 times 9/2, 2 goes into 4 twice. 2 times 9 gives you 18. And so if you add these together, we have 18 times 2, the opposite sides of the rectangle. We have 9/2 times 2. So we get 36 here. The 2's cancel, plus 9. Combine those straight down. We get an overall value of 45.